So K sub I is the force at degree of freedom I due to a displacement at degree of freedom J. So if you have a column or an element and we impose a displacement of 1 here. So let's look at this guy, right? So we got 6 degrees of freedom total. What you want to do when you assemble a stiffness matrix is all the degrees of freedom that you're considering, you set them all equal to 0, except for the one that you're playing with. So except for the J. So if we number them 1, 2, 3, 4, 5, and 6, I'm just literally grouping them by type. So let's impose degree of freedom 1, right? So what we want to do is we're going to keep everything else needs to stay the same. So this thing cannot rotate, nor can it displace. This node here is going to displace here, but it can neither move up nor rotate. So it's going to look like this. And therefore, this has to deform like this because it's literally a stick or something flat that you're shifting up. So this displacement is equal to 1. Okay. Now, what we want to do is what we need to find is what is the force at degree of freedom 1? What is the force at degree of freedom 2? What is the force at degree of freedom 3? 4? Well, that's tricky because the directions. Well, I like to draw it. I like to draw. So the way I do it, and a million different people will teach you how to do it. But this is what works for me is I look at this and I say, okay, I need to push this over to the right and it better be in the same direction, right? As the degree of freedom. If this thing were loose, if this were a stick in the air, what this would want to do is it would want to move over here, right? It's just going to move over to the side. I'm like, no, wait, you got to go back. So I got to push this node here. I got to push it back to its place.
Right.
Okay. And so that tells me the direction of that force. And so for me, all these Kij are the forces. So the Kij, all of them, are all the forces at the degrees of freedom, at the DOFs, that cause. Oh, and by the way, I'm recording this so that I'll send you a link to this, okay?
Okay, thank you.
So that cause the deformed shape associated with degree of freedom I equal to 1 and all others equal to 0, which is exactly what this shape here is. And so what are the forces that, in class, I had this, like imagine a ruler, right? You have a thin plastic ruler and that you try to move it upward, right? You're keeping it in place and you move one up. And so to keep it all from moving up, you got to apply a force here in this direction. That's easy. Just like you have to apply this force here in that direction. So this is K11 and this is K21. Then if this thing was free to rotate, what this stick would look like, if I were just holding it with the tips of my fingers, this guy would actually want to look like, so let's take out the actual deformed shape, right? So we decided we're going to move this guy. We need to push it here for it to be here and here for the displacements, right? Let me see if I can change colors. Okay, so we've got a node here and not a node there, sorry. The node is right here, right? So this thing would move like this if I could let it rotate, right? Imagine your pencil, you push your pencil up. So do this with your fingers. Hold your pencil with your two tips of your fingers. horizontal. It's easier to do it horizontal, right? So push one up. And so you feel yourself that you have to pull the other end down, but you see how it's a straight line?
Yeah. And you have to rotate it.
Yeah. And so to keep this from going like this and like this, right? That's how these guys have to be. So you have to apply a moment in this direction and a moment in this direction. So try that with your pencil. You kind of, you know, you have to bend it and apply that kind of a moment, like a torsion, to keep it that way. And so that is how I know that the moments go in this direction to keep this deformed shape, which is my final actual deformed shape as I want it, right?
Right.
Because it's zero displacement here, zero displacement here, and therefore I have a point of inflection there. Now this here becomes K5, 1, and this is K6, 1, right? In the axial, I don't really have to do anything. They're uncoupled. So, you know, except for the friction, there is no, you know, axial force in this direction. So those are actually zeros. Okay. So K11, K21, K31, K41, K51, K61. Now, if this is when the numbers, you have to use that cheat sheet. You know, just the basic one that tells you the 6s and the 12s and this and that, right? So we know that K11 is, but let's do first the signs actually, okay? So we decided that K11 is this value here. It's to the right, which is in the same direction as my degree of freedom, so that's positive. K21 is in the opposite direction. Remember, it's in this direction, right? And it's in the opposite direction of degree of freedom too. Therefore, that has to be a negative value. K3 and 4, we decided are 0. And then let's look at K51. K51 is clockwise, right? But degree of freedom 1, yep. And so that's negative. And what about this one? Same thing. It's clockwise, and therefore it's negative. And now for these values, so this is 6, is it 6 or 12?
12, I think.
Yeah. So it's 12 EI over L cubed. K21 is equal and opposite, so it's 12 EI over L cubed. And then the K5 and 6 are the 6 EI over L squared. Okay?
Right.
If I now do degree of freedom 2, it's kind of, well, let's do degree of freedom 2 only for the signs. Okay? So let's look at degree of freedom 2. We move it over. It has to be straight, right? Let me change color. So no rotation, and I just have a displacement. No rotation, no displacement here. So this is going to deform in this direction. So where's K11? Right here, right? No, I'm sorry. This is K22. It goes to the right. To keep this node from moving, K12 goes to the negative direction, which is good because it's supposed to be symmetric with K21, right? Then to keep this, this would want to go, oh my gosh, I can't even draw a straight line. Come on. Okay. So if we let this rotate, this would just move like this, right? So we have to apply a force, a moment in this direction and a moment in this direction. Is it in this direction? No, it's in this direction, right? Because we want to push this guy back this way.
Right.
And so this is going to be K62 and K52. And so this is positive, negative, This is negative, negative.
Mhm.
These are going to be the 12 EI over L cubed, and these are the 6 EI over L squared.
Mhm.
Okay. And
Yep.
the K3s, 3 and 4 are 0.
Right.
If we now look at the rotations, so now we've got our beam that looks like this. And what we're going to do is, and we always, this is what always gets me. So
Mhm.
degree of freedom 4. Oh, 1, 2. So forget 4 and 3 and 4, imagine axial, and it's only EA over L for axial. You're okay with those?
Yeah.
And off the diagonal ones are 0. So let's look at degree of freedom 5. And so it's counterclockwise. So we're going to take this line and we're going to rotate it a certain amount.
Mhm.
And it's got to be in counterclockwise direction because that's the direction of 5.
Mhm.
This end here has to not move, and this guy can't move. This top can neither move nor can it rotate. So
Right.
it's got to end up being like this, right? So let's take back our pen or pencil, or, I wish I had my ruler with me. So if I rotate this guy, my ruler's going to want to go that way, right?
Mhm.
So, well, first thing we know that the moment is in this direction, right? Our K455. So this is our K55. To keep this moment, to keep this from going so far out, we have to apply a force in this direction to get it back to here, right?
Right.
Because otherwise it's going to go way out there. So now, if I'm applying a force here, what this is going to look like is like this, right?
Right.
I managed to push it back, but wait a minute, I don't want it to rotate. So I have to kind of push, apply a moment in this direction
Right.
to straighten this out to look like this, so that now it's going to look like this.
Mhm.
And I know this is kind of a pain, and I have ADD, so that I have to go through this step every single time,
Mhm.
or I just use my cheat sheet of, okay, this is what these look like, but my brain has to go through this process every time I do it. Or you can memorize it, but it's always good to know and where it comes from.
Right.
And so that's what, now, because this force here is to the right, this is the only one that I can't do it intuitively. The force here has to be to the left to be equal and opposite.
Mhm.
Okay, so this is K55, this is K15, this is K25, and this is K65. Because those are my degrees of freedom that I had. I know that K35 is equal to K45, which is equal to 0. And just so that we put it down, K33 is, well, let's do those also, just so that, we've done the whole thing. Okay. So what do the forces look like? So K15, I'm going to just do this in a clean way. So K15, K25, K3, K4, K5, K6, 5, 5, 5, 5. All right. So what's K15?
Same thing as K51. So negative 60 over L squared.
Yeah, but you remember, don't look it up, because that is a way of checking. Okay, if you say, oh, it's the same as that one, well, what if I gotten that one wrong? And so this is when you want to go to that other cheat sheet. So there's 2 basic cheat sheets that you have is, and I'm pretty sure I give them to you guys. So the basic cheat sheets are, if you have a beam like this, and this is one deformed shape, these are the values that you want to know. So this is the 12, 6, 6, 12. And then the other one is, if you have this, it's 4 EI over L, 2 EI over L. I hate how this isn't 0. Okay. This is 0 rotation here. And then you've got a force of 6 EI over L squared and a force here of 6 EI over L squared. Okay. So these is like your cheat sheet. And this one even tells you what the sign of these things is. So then I go here and I go, oh, okay, what's the force that is where I'm applying the moment? So it is 6 EI over L squared, but in the negative direction because it goes to the left, right? 6 EI over L squared. Then I go, oh, look, it's exactly the same as K51. So I did it right. I never assume I did it right the first time. It's a good way to check it. So what's K25?
Is 12 EI over L cubed.
No, this is the cheat sheet you need to look
Oh,
at.
that's that one. Okay.
This is the deformed shape that we're working with. So this is what you should put
so
in your
6 EI.
Yeah. Positive or negative?
Positive.
Good. There is, I'm pretty sure I gave you guys a handout. Let me see.
You did.
I did a lot of like derivations and stuff, but there's one of them.
I think I saved it in my notes.
Good. This is this is what you want to have in your notes kind of thing, you know, all the degrees of freedom. Because then this is something that you want to carry with you and look back. And then with time and practice, you'll remember the 4s and the 6s. And I don't, but most people do. So I think the importance is to know what you can and can't do. And then that's what I do. I just make up for it and just, you know, processing it every time. Okay. So we go back here. The value was from here. It's a 6 EI over L cubed. Okay. And remember, the way I remember it is the value that associates a, so let me put, yeah, these were 12 EI over L cubed. This is L squared, EI over L squared. So the way I remember is the 12 EI over L cubed is a force to translation, right? The 6 EI over L cubed is a moment to a translation or a force to a rotation. So it's, you know, it's the diagonal term kind of thing, you know, the relationship between the rotation and force or displacement and moment. And then I have the 4 EI over L is where I apply the unit rotation. And then the 2 EI over L is at the other end.
Okay, that makes sense.
Okay, it's half of it. Now you're like, well, wait a minute. Aren't the sum of the forces equal to B equal to 0? Well, 2 EI over L plus 6 EI. So look at this. It's kind of cool. So if we take the sum of the moments here, let's see. 2 EI over L plus 6 EI over L squared times L is equal to, that goes away. It's 6 is 8 EI over L, yeah. And you have to do the sum of the, shouldn't that be equal to 0? Sum of the moment. Oh, because it's in the opposite direction. So this is in this direction and this is in that direction. So it should be, it gives you negative here. And so it's minus 4 EI over L, which is equilibrates the 4 EI over L. Okay. So I thought we'd come up with a whole new equilibrium. So that's how I kind of always check things. And I have to, just because I can't rely on myself to know it. So K35 is 0, K45 is 0 because those are the axial. So where do we find K55? What's the value for K55? I'll give you the cheat sheet.
It's the 4 EI over L.
And this is a good way to check your signs. Okay, it had better be positive. It has to be. Any diagonal term has to be positive. And so if you look here, it's like, okay, good, it is in the counterclockwise direction. I got that right. And now K65 is equal to what?
-2 EI over L.
Okay. Now, is it negative or is it positive?
Oh, it's positive.
Because I know with moments it kind of throws you off, but you literally have to just spin with it and go, yeah, it is going counterclockwise, so it's positive. Okay?
Yeah.
And so that's positive, and that's how we have it there. Now, be careful when you do the other term. So we've done that one. When we do the rotation here, right, this is degree of freedom 6 is counterclockwise. So now we're going to push this way, because we've rotated counterclockwise. This is what our deformed shape looks like. And so this is a positive moment, and that's a positive moment. Then I look here and I go, okay, this force has to go to the left, because otherwise this guy would just keep going that way.
Right.
And
So
therefore,
that's opposite.
yeah, that is the opposite. Okay. So now we've got, I'm on computer. So K16, K26, 3, 4, 5, 6, 6, 6, 6. All right, so what's K16?
K16 is okay, 6 negative and that's the opposite side. So it's -6 EI over L squared.
The good thing is the forces are always the same magnitude as each other at either end. But yes, it's negative. Now we go back and check and go, hey, look at that. We did it right. Okay. But this is where we got it from.
Okay.
And we see that it's going in the opposite direction. What's K26, this guy right here?
It is positive, no, 2, it's positive 6 EI over L squared.
And so don't look at there. So here, just look at it and go, okay, it's the way I draw them, and I like to just draw them the way they should go. And then that's going to tell me what the signs are. So yes, it's positive 6 EI over L squared. What's K36?
3 is, that's the axial, right? Yeah.
Yep.
So it's 0 and 0.
0, 0. What's K56, which is this guy right here?
Okay, 5, 6 is positive 2 EI over L. And then 6, 6 is positive 4 EI over L.
Yep. You can check it there, the sign, but you can also look at the figure here and go, okay, they do go counterclockwise. Now,
and these coefficients come from the virtual work method. You can use virtual work to solve for these, right?
Yeah, you have to, but we're gonna. For me, that was like 30 some years ago. So you can start from here. You can start that those are given. Chopra's book gave them to you. These are universal and are going to work everywhere and anywhere.
Okay.
There's special ones when you have a pin at the other end, which is just a way of, not dealing with that degree of freedom. But personally, I always end up just dealing with that degree of freedom and just having a bigger matrix, and then I can condense it out if I have to. But I will just deal with that degree of freedom because I can never remember the 3, the blah, blah, there's no symmetry in that. So now let's, just for completeness, let's do degree of freedom 3 and 4. So now what we're going to do is we're going to take, I'm just going to resketch it here. 1, 2, 3. So it's 1, 2, 3, 4, 5, and 6. Okay. So let's take degree of freedom 3 and move it by 1. Right? We're going to move it up by 1 because that's the 3rd degree of freedom. So we're looking at axial, right? So now to push this node up, we have to apply a force upward. Right? Now to keep this, where would this node want to go? This node is going to want to go up that way with it, right?
Yeah.
So what do we have to do to keep it in place?
And push downward.
Downward. So now, K, do we have to apply a lateral force or moment? No, those are all 0, right? So K13 is equal to 0. K23 is equal to 0. But K33 is equal to this force right here. So it's
EA over L.
EA over L. What's K43?
Negative EA over L.
Yep. And then K53 equals 0. K63 equals 0 because we don't need any moments to do that. And so if we now look at degree of freedom 4, and now we move it not downward, now we're going to move it upward, right? It's always positive up. That's what we have to, it just, I start doing it downward just because of symmetry. And so now we've had to push this guy up to move it upward. Well, this node would want to go up with it, right? And so we have to apply a force equal and opposite to keep that node from moving downward. And so this is positive EA over L, and this is negative EA over L. Okay. And now we've assembled the full stiffness matrix.
Okay, that makes sense.